Hello everyone, my name is Tom Oxberger and I'm a software engineer here at Anaconda where I work on open source packages like Pandas. And today I want to talk about an example of using Pandas Nullable data types to work with missing data. So first of all, what are nullable types? If you've used Pandas for a while, you know that dealing with missing data can be somewhat challenging. There's the just inherent issues with missing data, like, what does missing even mean? Why is this particular value missing? Was it missing in the data set? Has it been introduced as some operation in Pandas? But beyond those inherent complexities, Pandas add some additional complexities that mainly come down to its type system not really working well with missing data, at least not for the kinds of workloads that most Pandas users care about. For example, if we're going to make a toy data set here, a couple of series that are using int64 data types, using NumPy's default. And when we do an operation like addition between these two series, we'll see that a missing value is introduced. That's because the first series didn't have a value for C, so we do an alignment, we reindex the S1, and that introduces a missing value. It specifically introduces nan, which is a floating point number. That casts the entire series from integer to float, which makes the result become a float. So this is kind of, sometimes it's kind of annoying. Say you're doing some sort of downstream operation where you want to format your output for some report. We're going to do some padding of that result to the width of 3 with some fill character. And we see that thing's messed up because this 0.0 has thrown off the width of our result. So maybe you just include a bit of stripping of those nonsense characters, and then we can do our padding like we wanted. So that's not the end of the world. It's a bit annoying, but you can also run into more serious issues where the casting from integer to float can cause actual changes in the result of downstream computations. That can occur because if you have large enough integers, they can't be precisely represented as a floating point value. And it can get to the point where it actually affects computation. So in this case, we're going to have a couple of integer columns, data frames with integer columns. So df1, this value a will be int64 by default. And then we go and do an outer join with df2. And since the join IDs don't overlap perfectly, there's going to be an outer join there. And we'll have to cast those integer columns to floats. Again, inserting nan in the places where there weren't any values before. Inserting that nan forces the casting to float, which caused the precision issues. And so now if we do something like a diff, on the original one, the difference here between these two rows was 1, like you would expect. But after doing the outer join, we can see that the diff is apparently 2, which is not what we would expect. And that just comes down to the difference, the inability to represent these large integers as floating point numbers. Another place you'll commonly run into this is when interacting with other systems, like the file system or like a SQL database. If they have different type systems, which they will, then they're going to complain. In this example, we'll generate a couple of CSV files, data0 and data1.csv, write those to disk, take a look at it, and we have a couple of those. And now we want to use dash data frame to read in this collection of CSV files. Dash data frame, again, it takes a directory of CSV files or a glob string, and we can go ahead and run this, and we'll see that we get an exception. And that comes from dash data frame requiring a consistent schema across the files that it's trying to read in. And it's inferred a int64 for the first file because that's what it checked. And when it gets to the second file, it notices that value is apparently float64 now. And that just comes down to there being a missing value in the original data frame that we wrote to data1. So you can see here this kind of inconsistency, casting otherwise integer columns to floats is causing issues in systems like Dask. It'll also affect things like ToSQL will blow up as well. If you try and write something that's been cast to float, to an integer d-type column. It's not just integers that are affected. This type of casting also affects Boolean data. So in Pandas, if you have a Boolean column and do some operation like a reindex that introduces missing values, you'll get back an object d-type. So Pandas will insert this nan, which is a floating point value, and it'll cast to object d-type to avoid casting the Booleans to floats. This has a different set of trade-offs. It's preserving the types of individual elements, but the object d-type is going to be much slower. And confusingly, object d-type can contain anything. So object d-type is what Pandas uses for strings as well, so it kind of muddied the waters there about what exactly is stored in object d-type. Is it strings? Is it anything? And even when you intend to store just strings, you can end up with other stuff in your object d-type array. Things like lists of whatever and integers. So the root issue that Pandas is kind of facing here is that every element in a NumPy array has to have the same type. And NumPy doesn't have a missing value for integer or Boolean data like it does for floats or for datetimes. So Pandas has to make some choice. Do we just not let you store missing data, which isn't very satisfactory, or do we force you to, or implicitly cast, typically to float or object? Fortunately, newer versions of Pandas have some better alternatives, and that's the new nullable data types. So in this case, we're going to explicitly create a couple of series using Pandas integer d-types, nullable integer d-types. And now when we do the operation, adding the two series here, we'll see that we get back NA. So again, the series indices don't overlap perfectly, so Pandas is going to align. That's going to introduce an NA where there wasn't a value before. And we've preserved the integer d-type here. This is Pandas nullable integer d-type because, and you can tell that because of the capital I here. So we have nullable integer types for integers, like we just saw, for Booleans, and for strings. And each of these natively support missing values with the pandas.na scalar. So I want to talk a bit about the differences between pandas.na and nan. So nan, they're similar in the sense that they're both going to be involved in operations like fill NA and drop NA and is NA. They'll behave similarly there. So they're both used to represent a value that is missing. But there are some differences, especially around meaning and behavior in operations. So nan is defined in this IEEE spec that defines floating point arithmetic. It's a specific floating point value that's typically used to represent the result of an undefined operation. So if you do something like 0 divided by 0, by definition, in the spec they say that that should be nan. It'll also come up in things like taking the square root of a negative number. There's also, and this is mentioned in the spec, but it's like a secondary purpose, it also mentions missing data. And that means many more things. Like it could mean like this value was recorded and it's known, explicitly known to be missing. Or it could just be there's supposed to be data here, there's not for whatever reason, and so we're going to mark it as missing. Or it could be the result of a bad operation or any other number of things. So this kind of overloaded meaning has caused problems in the past. Beyond just the complexity of what is NA, what is missing, there's the behavior and operations. nan has some not exactly obvious behaviors when it comes to comparison operations. So by definition, nan always compares false to everything else. So if we have a Boolean series here, we'd like it to be Boolean. We also have this missing value here. So it's been converted to object by pandas. If we do a comparison with 1, we'll see that nan is not greater than or equal to 1. It's also not less than or equal to 1 since it's always false. And it's also not equal to itself. And this is a perhaps surprising behavior, but I mean, you can get used to it. I think it's also just not very useful. The Pandas maintainers have found that propagating NAs in comparison operations is generally more useful and more in line with what people expect when they first come to Pandas. So that's what we've defined for this Boolean data type, for pandas.na, which is used in integer, Boolean, and string. If you use it in comparison operations, the NA will propagate. So is this value NA, is it greater than or equal to 1? Well, it depends. It could be if it's equal to true, if it happened to be equal to true, and it might not be if it's false. So we don't know, and so we propagate that NA. Likewise for equality, and also for logical operations like logical OR and XOR. We use what's called clean logic or three-value logic that's implemented in most SQL systems. So the result here is going to be NA because we don't know what it should be. So in addition to, I think, this more useful behavior in comparisons, which is consistent with the behavior in arithmetic operations, Pandas NA and its nullable D types will correctly handle this issue that we had before when we were doing this join between two large data frames, two data frames with large integers. So in this case, we're going to specify Pandas nullable integer D types. And we're going to go ahead and do the join, again, the outer join, and we've introduced the NA values here where there weren't any values previously. But now when we do the diff, so we'll select value A and we'll take the difference between this value and this value, and you'll see we'll get the result that we expect. We get 1, which is good. And then we saw that Pandas object D type, which we use by default for strings, has this unfortunate behavior where you can store anything because everything in Python is an object, so anything can go in an object D type array. But if we explicitly ask for a string array and try and set a non-string in there, Pandas will protect us. We'll get a value error there saying that you can't set non-string values into the string array. Finally, looking at performance, Pandas nullable integer types can be more performant, especially if you're comparing it to the Boolean object D type case, where introducing missing values has cast from Boolean to object. So in this case, we're going to take a 10 million row series of trues, falses, and missing values, and we'll convert it. This will be object D type, thissobj. And we'll convert it to Boolean as well to compare the performance. First of all, in terms of memory, the Boolean version, the nullable Boolean version, is going to take up much less memory. Object D type's taking 300 some megabytes. The Boolean version is taking up 20 megabytes. Operations will be faster, so we can do something like a reduction, taking the mean to find the proportion of values that are missing. With the object D type, that took about 800 milliseconds. With the Boolean version, it took about 200, so about a 4x speed up on this particular example. Logical operations will have a similar sort of speed up. Do recall that these will be giving different values, since in this version, the logical OR will evaluate to false, and in this version, the NAs are going to propagate. But we think that that behavior is more useful anyway. So in addition to being more useful, it's also much faster. This first one's taking quite a while. And that's just because of, we're losing, by using the object D type, we lose all of the benefits that we usually get from NumPy by moving these operations, these element-wise operations, down to a fast for loop in C. Since we have Python objects, we keep having to jump back out of C up into Python to do the operation on each individual element. So if you're using Pandas, if you were using Pandas old D types, integer D types, and you wanted to avoid casting to float, so you manually cast to object, you would see similar sort of speed ups by moving to Pandas nullable integer D type. Okay, so for next steps, if you are interested in using these nullable D types, you can check out the convert D types method that we saw earlier. That'll take any of the normal D types like NumPy's int64, float, int64, Boolean, and convert them to Pandas nullable D types. Right now we have nullable D types for integer, Boolean, and string. But that's going to be expanding to more D types in the future, most notably including datetimes. And if you're already using these file formats like Parquet will preserve the nullable D types. So if you have nullable D types, you write them out to Parquet, you'll get them back when you read them back in. If you are interested in learning more, check out Pandas documentation on working with missing data. Thanks for watching.